Hey everyone, welcome back to our channel. Today we're going to talk about the physics paper 4 9702, which is the CIE A-levels physics, variant 4.2 from the October-November 2024 series. So let's go to the first question. All right. A metal wheel consists of an axle A, 8 spokes, and a rim. Point X is on the rim at the end of one of the spokes. Rim has the radius of 0.85 meters. Wheel is rotating clockwise. So clockwise means this way, with an angular speed of 140 radians per second. For point X, determine the speed. Okay, so we're familiar with this formula for the speed. V is equal to R omega. R is 0.85 times by omega is given as 140 radians per second. So 0.85 times by 140, that is 119 or almost 120. Almost 120 meter per second. All right. Centripetal acceleration. So centripetal acceleration we can find out by v squared over r. V we have already found out. You can use 119 also. You could use the r omega squared also. Either way it's fine since we were given r and the omega, so it would be better if we use those values instead. So if we use the r omega squared, we can use 0.85 times by 140 squared. So 140 squared, that gets us 16,660. Yeah, 660, right. So we need it in two significant figures. So that would be 17,000 meters per second. Right. And yeah, okay. There is a uniform magnetic field of flux density 0.18 Tesla into the plane of the paper. State Lenz's law of electromagnetic induction. All right. So just to show you, just to introduce to you again, we did that in the previous video also, is our grade boosters. So grade boosters we specifically made for A2, AS. We have a different docs. Grade booster pack for A2 contains the graphs, definitions and formula, which is basically a rundown of all the definitions and formula, important definitions and formula. Then we have important derivations. We know that some derivations are listed in the syllabus, some of them come again and again in the exams. So those are also listed over here. Also, we have done those for you. You can read through them. And last but not the least, frequently examined questions. These are mostly theory questions, which over here you can find out how we have actually made it is that syllabus points on the left hand column, the questions according or relevant to those syllabus points, their answers align with the marking schemes and the years that they are asked again and again. So since we're talking about the Lenz's law, let's go and search for the Lenz's law. A Lenz's law. Yes, okay. State Lenz's law of electromagnetic induction. It states that the direction of induced EMF is such that it opposes the change in magnetic flux that produced it. That's it. That's it. And on the right hand side, you can see that these were the years that they were asked. It like obviously this is not an exhaustive list, but these were the major years that uh, were asked. Okay, so it states that the direction of induced EMF is such that it opposes the change in magnetic flux producing it or producing it. Okay. Show that the time taken for the point X to complete one revolution is 45 meters per second, milliseconds. So we can find out using the angular velocity, sorry, 2 pi over t. So t is 2 pi over omega. Omega is given as 140, so 2 pi over 140. So 2 pi divided by 140, that is this, seconds, 0.04488 seconds, which when you convert it into milliseconds, 1, 2, 3, this becomes 45 milliseconds. Calculate the magnetic flux cut by the spoke X during one revolution of the wheel. Okay, so magnetic flux cut, okay, so magnetic flux is phi BA. So magnetic flux density, which is given to us as 0. Wait, where was it? Oh, sorry. Oh, 0.180 Tesla. Okay. 0.18 Tesla, and the cross-sectional area is given by pi r squared. Pi times by the radius is given 0.85. Okay. Square. Okay. So 0.18 times by pi times by 0.85 squared. So we have 0.408 or 409, let's call it, Webers. You could do 0.41 also, Webers. Determine the magnitude of electromotive force induced across the spoke AX. So spoke AX is this. This is your A, this is your X. Okay. So we need the rate of change. So according to the Faraday's law, the EMF is equal to the change in flux over change in time. So change in flux is 0.41. Time, we found that to be this value. So 0.04488. So divided by 0.04488, we get 9.1 volts. So induced EMF is 9.1 volts. If we have done 0.045, we would have gotten also the same thing. So absolutely fine. Use Lenz's law to explain whether the potential is higher at the end A or end X of the spoke. Okay, now to understand this question, we need to do it a little bit carefully because there's a difference of opinion among the teachers about this question, and there's not a lot of clarification in the marking scheme. So there are a few things we need to lay down or revisit before we answer this. The first thing is the difference between EMF and potential difference. So we know from the AS that EMF is the energy converted from other forms to electrical per unit charge by the source, by the power source or EMF source. Potential difference, on the other hand, is the energy converted from electrical to other forms. Per unit charge around the circuit. Oh, sorry. Which means that when you have the EMF source or the power source, it is providing energy to the charge, aka raising the potential of charged carriers. But on the other hand, when the charge is moved outside the source, they are losing that energy. So charges lose energy as they move around the circuit, right? And we also know that from the graph of potential, if you have two opposite charges, plus q and minus q, the graph actually goes like this, from higher potential to lower potential, and the negative one, because from positive to negative it will go that way. So that would be the direction of the positive charge also. So if you place a positive charge over here, it will go to the negative charge. We are already familiar with this. Now, which means that if you combine these two together, so for example, you have a battery over here, plus minus, and you have a circuit. You have a resistor over here, R, you have some current flowing. We already know this is the current direction. So this is the conventional current direction, which is from higher to lower potential. But care must be taken that this is outside the battery, outside the power source. But inside the power source, it will carry on in this direction because we just said it is raising the potential of the charges. So current would still be in this direction, inside the battery, inside the source. Okay, so inside the source, it would still be in this direction. Okay, now going back to this question over here, how do we determine the original motion over here was in this direction? So this means that there's a, according to the Lenz's law, the force produced, or the force, opposing force, would be anti-clockwise. So this is the motion, this is the opposing motion. So that way the force would be this way over here. This we're good with. I hope everybody understands this. Why? Because let's see the Fleming's left hand rule also. So Fleming's hand rules, let's clarify them also, how we are actually using them over here. If we use the left hand rule, so thumb points to the direction of force produced force produced. Index finger points to the direction of magnetic field, and middle finger points to the direction of current, which we are already familiar with this. But in the right hand rule, things are opposite. Thumb is the direction of motion of conductor. Index, as before, is the direction of magnetic field. And middle finger, finger would be the direction of current induced. Now notice one thing. These two are exact opposites. These two forces will be exact opposites. So this is the motor rule and this is the generator rule, basically. So in this case, we can use right hand rule also, left hand rule also. Why? Because once the current is induced, conductor becomes a current carrying conductor in the magnetic field. Okay, so Fleming's left hand rule can be used also. So Fleming's left hand rule can be used to determine direction of force produced. Otherwise, just simply use the right hand. So otherwise, Fleming's right hand rule can be used to find direction of induced current. Now, the problem is, what current is this? Is it inside the power source or outside the power source? So this current is basically inside a power source now. This has become a power source, EMF source, basically. So as we said, current inside EMF source goes from low potential to higher potential. Now let's go back to the spoke. So if force is upwards, we have determined the upwards force now. This is your force. Field is inside the inside this. So according to the left hand rule, the current would be this way. Okay, so this is the Fleming's left hand. But if you want to use the right hand, either way you will get the same thing. So motion is downwards. This is your motion. Magnetic field is into the page. So if you use the right hand rule now, you will get the current also in this direction. So this means undoubtedly over here that the current is moving this way. However, the question was whether end A is at a higher potential or end X. Since this is now a generator case, X is at higher potential. And this is at lower potential. So, which further means that if we were to, connect these 2 points with a circuit, this is your R over here, that the current would continue flowing in this direction and go back or like this. So this is what the question is asking. So we go back and answer this. Okay, so we will say that Lenz's law suggests EMF will be induced to oppose the clockwise motion using Fleming's. You can use both right hand, left hand, either way. As you saw, we got the same answer. Left hand rule. Current will flow from A to X. Hence, X is at a higher potential. That's it. That's it. That's all we have to say. Now, question number 2. The Sun may be considered a uniform sphere of mass 1.99 10 raised to power 30 kgs and a surface temperature of 5780 Kelvin. A probe with a mass of 2.63 kilograms moves in a straight line towards the Sun. Okay? When it is at a distance x from the center of the Sun, the probe measures the gravitational field g due to the Sun and radiant flux intensity radiation of the Sun. Okay, so mass, temperature. Okay, define gravitational field. Now we can go back and see what we wrote in the FAQs. Now, if we go up, just to show you that we have got you covered over here, gravitational field. Sorry. Right. Vector quantity representing the gravitational force per unit mass that would be exerted on a small test mass at any point in space. So what's important over here is the gravitational force per unit mass. Vector quantity that represents gravitational force sorry per unit mass at any point in space. Okay, for the position of the probe where x is equal to this, calculate g. So G is, we know, found by Gm over R squared. Since this is center to center distance, so we can use that. So G is 6.67, 10 raised to power minus 11. Mass of the sun is given as 1.99, 10 raised to power 30 kilograms, divided by R, which is given as 1.47, 10 raised to power 11 whole square. So we put this into this, 6.67 times by 1.99 divided by 1.47 squared. Now we deal with the powers of 10. Minus 11 plus 30 minus 22, because 10 raised to power 11 whole squared becomes 2. So this, if you convert it into the standard form, becomes this: 6.14, 10 raised to power minus 3. Determine the gravitational potential energy of the probe. So that is just simply m phi, which is m times by minus gm over r. Okay, so this is the small m is the mass of the probe, which is given as 2.63 kilograms. So 6.67, 10 raised to power minus 11 times by a mass of the probe, mass of the sun, divided by R, which is given as 1.47, 10 raised to power 11, and the minus sign over here. All right, now we need to calculate this. So 6.67 times by 2.63 times by 1.99 divided by 1.47 times by, now we deal with the powers of 10, minus 11 plus 30 minus 11. You get 2.37, sorry, minus 2.37, 10 raised to power 9 joules. Show that for any particular value of x, the numerical values of g and f are related by this, where m is the mass of the sun, L is the luminosity of the sun, g is the gravitational constant. Okay, so we know that f is L over 4 pi. We don't need d squared over here. We know that that is the r squared this time. Oh, sorry, x, because x is given as the distance, so x over here, x squared. So we just need to replace out x over here, right? So x squared over here is given as L over 4 pi. We also know that g is equal to gm over x squared. So x squared over here is gm over small g. All right. So we substitute for x squared. Actually, in this question, we can actually do this over here. 4 pi f over here. So we can substitute for x squared in this because we need it in this form. G is equal to, in the form of g. So gm divided by L over 4 pi f. So this becomes 4 pi gm over L, and f also goes in the numerator, so f equals to g. That is your simple over here. All right, figure 2.1 shows the variation of g with f. Okay, so basically this thing shows over here that g and f, small g and f, are directly proportional to each other. Determine a value for luminosity L of the sun. So luminosity will come from the gradient. So we need the gradient over here. So gradient that is equal to 4 pi gm over L is given by, we need any two values over here. Since this is directly proportional, one can be 0, 0, but we need just one more value. Let's see. Let's zoom in. I think this value would be appropriate. So 1.6, 1.7, so this is 1.65, and this is 5, 6, 7, no, sorry, 5, 6, 7, no, wait, sorry. So 4 is divided by 10, so that means each box is represented by 0.4. So that means 8 divided by 0.4 is represented by 20. Oh no, sorry. Sorry, no, no, no. Each box, so 0.4 times by 8, that would be 3.2. So 4 plus 3.2, which is 7.2. Okay. So this is 7.2. So this one would be 7.6, and then that would be 8. So 7.2. So so we have gradient equal to 7.2 10 raised to power minus 3 divided by 1.65 10 raised to power 3. So for luminosity, we just cross multiply. So we have 4 pi times by 6.67 10 raised to power minus 11 times by mass, which is given as 1.99 10 raised to power 30 times by 1.65 10 raised to power 3 divided by 7.2 10 raised to power minus 3. So let's do this. So 4 pi times by 6.67 times by 1.99 times by 1.65 divided by 7.2 times by 10 raised to power minus 11 plus 30 plus 3 and minus minus 3. So that means plus 3. So we get luminosity 3.822 10 raised to power 26. So 3.8 10 raised to power 26. Luminosity is in watt, so watt. Use your answer in C to determine the radius R of the sun. Over here, we will use the Stefan-Boltzmann law. Oh, sorry. So L is equal to 4 pi sigma R squared T raised to power 4. So that's what we need over here. We need the radius. So L divided by 4 pi sigma is the Stefan-Boltzmann constant, T raised to power 4, luminosity 3.8 10 raised to power 26 divided by 4 pi. Stefan-Boltzmann constant, we will go quickly and check from the booklet. 5.67 10 raised to power minus 8. 5.67 10 raised to power minus 8. The surface temperature was given as 5780 kelvins raised to power 4. Okay, so Sorry. Uh, okay, never mind. Damn it. Okay, never mind. We can use 3.82. So 3.82 divided by 4 pi divided by 5.67 divided by 5780 raised to power 4 times by 10 raised to power 26 plus 8. We get this value for the square, 4.8 10 raised to power 17. So therefore R will be the square root of 4.8 10 raised to power 17. So square root of answer, that is 6.93 10 raised to power 8. So 6.9 10 raised to power 8. And that's it. All right, moving on to the next question. Specific latent heat. So specific latent heat is also very easy definition. That is just energy required to change the state of a substance at constant temperature. So just to show you that this is exactly, yeah, the amount of energy required per unit mass to change the state of specific substance without changing its temperature. So amount of thermal energy required per unit mass to change the state of a substance at constant temperature. That's it. A dish containing 7.2 times by 10 raised to power minus 5 meter cube of a substance rests on a laboratory bench. The substance is initially a liquid of density this, atmospheric pressure is this. Liquid is heated at its boiling point so that it completely vaporizes. The increase in internal energy of the substance during this process is 17.6 kilojoules. Final volume of the vapor is this. Show that the magnitude of the work done on the substance when it vaporizes is 1.7 kilojoules. Okay, so this all is happening at a constant pressure. So we can use the work done, constant pressure times by change in volume. So 1.0 10 raised to power 5 times by change in volume is going from 7.2 10 raised to power minus 5. Sorry, this would be the smaller volume, sorry. 0.017 minus this. That's all what we need over here. So meter cube, and pascals, right, okay. So we have 10 raised to power 5 times by the difference between 0.017 minus 7.2, 10 raised to power minus 5. We get 1.69, oh sorry, 692 10 raised to power 3, so which is approximately equal to 1.7 kilojoules, because this is 10 raised to power 3 over here. Okay, use the information in B1 to calculate the thermal energy Q in kilojoules supplied to the substance to cause it to evaporate. Okay, so we will use over here the first law of thermodynamics. which is the increase in internal energy is equal to the increase in thermal energy plus the work done on it. This is expansion, so this is going to be negative work done. So change in, sorry, uh, change in increase in internal energy is given as 17.6 plus 17.6. Increase in internal energy, that's what we need to find out. And the work done is minus 1.7 10 raised to power 3. Or we can do 6928 also. Let's do 6. Actually, it's absolutely the same thing. So, oh, sorry, my bad. Again, I forgot. 17.6 plus 1.7, 10 raised to power 3. So we get 1.7. Oh, wait, sorry. This is 17.6 is also in the kilojoules. So, 17.6, 10 raised to power 3. So that is also in this. So what we can do is we can put brackets around these two. So we get 1.93 10 raised to power 4 joules. So in kilojoules, it would be just without the 10 raised to power 3. We could have done this 19.3 kilojoules. All right. Use your answer in B2 to determine the value for specific latent heat of vaporization in kilojoules per kilogram. Okay, so we need it in kilojoules, so we are going to be using this basically. So latent heat of vaporization would be Q over mass in kilograms. So 19.3. Now we need the mass. Do we have the mass? No. Okay. So we have this density and initial volume over here. So we can use that because mass is going to stay the same. So 710 times by 7.2, 10 raised to power minus 5. So divided by 710 divided by 7.2 times by 10 raised to power 5. So we get 3775, 3.775, 10 raised to power 2. This would be 377, or it's roughly about 380 kilojoules per kilogram. So roughly about 380. All right, the substance in B has a specific latent heat of fusion F. Suggest and explain whether latent heat of fusion is likely to be less than, same as, or greater than the answer in this. Okay, so latent heat of fusion is almost always less than that of latent heat of vaporization because you need a significant increase in separation. So from solid to liquid, there is less, like there's an increase in molecular separation, but not that much. But for gaseous state, you need a very significant increase in molecular separation. So you're overcoming intermolecular forces by a significantly larger value. So you will have to increase the internal energy of that substance by quite a lot. So to answer that, we also, again, we have got you covered over here. Specific latent heat of vaporization is much greater than that of fusion because vaporization not only involves breaking of intermolecular bonds, but also increasing the spacing between molecules to a much greater uh, extent than fusion. This was a question that they asked for specifically in terms of spacing of molecules. We also have another scenario where they asked for in terms of internal energy. So let me show you that definition also. We can combine these two. Where did this go? Yeah, okay, this one. Specific latent heat of vaporization is greater because of overcoming greater intermolecular potential energies compared to specific latent heat of fusion. Kinetic energy remains unchanged during the respective change of state because temperature is the same. Thus, it involves a large increase in internal energy, requiring more energy to break intermolecular bonds and increase uh, molecular spacing significantly. All right, so let's go back and rewrite this. So perspective is that we are comparing this with latent heat of fusion. So we can say that latent heat of fusion would be less than LV because it involves much smaller change in molecular separation. Sorry, because a fusion involves, because fusion involves much smaller change in molecular separation than vaporization. Uh, Thus, fusion requires less energy to overcome intermolecular forces and subsequently, and therefore, oh, sorry, less increase or less change in internal energy. That's it. All right. Let's move on to question number 4. Okay. State 3 of the basic assumptions of kinetic theory of gases. So let's see this over here. Uh, these are easy. You will have to memorize that. These. So volume of the gas is negligible compared to the container's volume. No intermolecular forces except during collisions. Gas molecules are in constant random motion. Collisions involving molecules are perfectly elastic. Gas molecules are obey the laws of Newton's laws of motion because we are assuming them to be small spherical balls, rigid spheres. Average kinetic energy of the molecules is proportional to the absolute temperature. So we can use any of the three over here. So we can say that the gas molecules are in constant random motion. No intermolecular forces exist. Oh, sorry. Except during collisions and uh, collisions between molecules also are elastic. What else? What else? Volume of molecules. Sorry. Is much smaller than the volume of container. That's it. All right. Explain how the molecular movement causes the pressure exerted by gas. So we also wrote this over here. All like, uh, let's say over here. Yeah. Okay. This one. So gas molecules move randomly and collide with the walls of the container. Each collision exerts a tiny force on the wall, just a like, force on the wall due to change in momentum. Pressure is the result of continuous force per unit area caused by many such collisions. So exactly the same thing we can write over here. So gas molecules move randomly and collide with the walls of container. Each collision exerts a force on the wall due to change in momentum. So the pressure is the result of continuous force per unit area due to multiple collisions. By a number of particles. Okay, now figure 4.1 shows the variation with thermodynamic temperature of the mean square speeds of the two gases. Okay, so we see over here that this is a proportional response over here. So mean squared speed is proportional to the thermodynamic temperature. Now, let's see over here. Figure 4.2 shows the variation with T of the product PV for samples of the two gases, where P is the pressure of the gas and V is the volume of the gas. So this is also showing that the product PV is proportional to T, and this is these both of these relationships, these proportionalities, they are evidence of ideal gas behavior. So state three conclusions about the gases and their samples that may be drawn from the figures. Conclusion may be qualitative or quantitative. Okay, so we just need to state it. We don't need to explain the reasons for this. So both gases are ideal gas. Okay, now let's examine this a little bit more detail over here. So we know what's the relationship between mean squared speed and temperature. That is 3 kT over m. which means that the 3k over m is the gradient over here. So if we examine the values over here, 2 is divided in 10 parts. So that means each graduation is, each mark is 2. So 0.2. So this means that this is 2.5 and this is 5. So we can see that the gradient is a gradient of x is double than the gradient of y over here. Okay, so we don't actually need the values for this. 5 divided by 4. We can actually do that because this is 0, 0. So 5 divided by 400, 2.5 divided by 400. So we don't actually need the full values over here. So let's write over here that 3k over m, let's call it mx, mx is equal to 5 over 400, and the 3k over my is 2.5 over 400. Now, when we equate the 3k, because they are obviously equal, even we can like cross multiply this thing. So 3k times by 400 is equal to 5 times by mx equals to 2.5 my. So we can just focus on this because the other side would be just constant. So mx over my would be 2.5 over 5, which is 1 over 2. Furthermore, we can say that my is twice the mass of x particle. So this is one conclusion we can say. So the mass of particle of gas y is twice the mass of particle from gas x, Now let's look at the other one, PVT. We know the relationship. That is just simply PV is equal to NKT, which means that N and K are the gradient over here. So both N and K, so that would mean that the N is different over here. So let's see this again. This is 0.9 and 2.5, 2.6, 2.7. Okay, so we can say that the Ny times by K is equal to gradient 2.7 over 400, and Nxk is equal to 0.9 over 400. So K and 400 are basically equal over here. So so K of K 400K over here is equal to 2.7 over Ny equals to 0.9 over Nx, which means that Nx over Ny is equal to 0.9 over 2.7, which is 1 over 3, which further means that Ny is 3 times the number of Nx. So this is another observation over here. So we can say that the gas Y contains 3 times more as gas X. Oh, sorry, not three times more, three times as particles, three times particles as that. You could say as many. Okay. Now, on to the question number 5. Figure 5.1 shows the pendulum consisting of a metal sphere suspended by a thin string. Sphere undergoes small oscillations at about its equilibrium position. The oscillations may be considered to be simple harmonic. Figure 5.2 shows the variation with time t of the displacement x of the sphere from its equilibrium position. On figure 5.1, draw an arrow from the center of the sphere to represent the direction of resultant force acting on the sphere when its position is shown. So restorative force basically would be towards the mean position going this way. Do we need to label it? No, we don't need to label it. Okay. Now, the mass of the sphere is 0.15 kg. State the amplitude of the oscillation, so we can see that from over here. 0.0. This is 0.015. Oh, sorry, 0.015, and this would be 0.016. Okay, so 0.016. Determine the angular frequency of oscillations. So angular frequency of oscillations comes from 2 pi over time period. So time period we just need to deduce from over here. So time period is 0.4 simply. So 2 pi over 0.4. So 2 pi divided by 0.4, that is 15.707. So roughly about, you could say 16 radians per second. Two significant figures. Calculate the total energy of the oscillation. So total energy of the oscillations, remember the formula, half m. This is equal to the maximum kinetic energy. So half m omega squared x naught squared. So x naught is the amplitude. So half mass is given as 0.15. Omega is 16, we just found out. And x naught is 0.016 squared. So 0.5 times by 0.15 times by 16 squared times by 0.016 squared, we get, let's turn this into scientific for the standard form, sorry. This would be 4.9 10 raised to power minus 3. So 4.9 10 raised to power minus 3 joules. On figure 5.3, sketch the variation with x of the kinetic energy, k of the sphere. Okay, so the formula for the kinetic energy goes like this. So half m omega squared, because v is equal to, v squared is equal to omega squared x naught squared minus x squared, or like omega squared x naught squared minus omega squared x squared. So when we replace out the v, half m v squared over here, so this turns out to be half m omega squared x naught squared minus x squared. So that means that we have a total energy 4.9 over here. So 4.9, if this is 5, 4.9 would be somewhere over here. So this is the maximum point over here. So somewhere over here is the maximum point. So like almost 5, you could say. So now this is going to be inverted parabola graph, basically like this. So the amplitude is going from 0.016. So 0.0, this is going to be this and this thing. So the graph actually goes, let's do, okay, it's fine. Blue. So it goes, sorry, it goes like this. And it goes like this. That's it. And you can see that from our grade booster. So graphs. Yeah, okay. So the red one over here, that is the kinetic energy. So that's part it. We can delete this one because that signifies the maximum kinetic energy. Right. Okay. Okay. So state Coulomb's law. So it is very similar to uh, Newton's law of gravitation. Only the wordings are changed. So it states that the electrostatic force of attraction or repulsion between two charges, point charges, is proportional to product of their charges and inversely proportional to square of their separation. Okay, so figure 6.1 shows an isolated hollow conducting sphere that is positively charged. On figure 6.1, draw field lines to represent the electric field outside the sphere. So basically, you will have radial lines, the lines going outwards from the circle. So this, okay. So we can have these lines also. That's it. All right. Outwards because it's the positively charged sphere. Okay. Figure 6.2 shows the variation of electric field strength with distance x from the center of the sphere in B. Okay. Determine the radius in centimeter of the sphere. Okay. So we know that for a charged sphere, electric field until the radius, until the surface is zero. That is the evidence of the fact that the charges inside, they did not move. That is also the reason why uh, the potential up until the surface would be constant, because there is no potential difference, no movement for charges required. So we go back over here with point charge, sorry, surface, sorry, charge sphere. So like this, electric field is zero, but potential would be constant. So no potential difference, no electric field. Okay. So radius would be up until this point. So this appears to be 3. This would be 3.2 centimeter. Calculate the charge on the sphere. So calculate the charge on the sphere. Charge on the sphere can be found from this. So that is 2.2, 10 raised to power 5. Okay. So electric field strength can be found from KQ over R squared. So 8.99, 10 raised to power 9, 10 raised to power, Q we actually need to find. R is 3.2 times 10 raised to power minus 2 squared. And this is equal to 2.2 10 raised to power 5 newtons per coulomb. Now we just need to cross multiply for Q. So 2.2 10 raised to power 5 times by 0.0032. Oh, no, sorry, just 1 0. Squared divided by 8.99 10 raised to power 9. Okay, so 2.2 times by 0.032 squared divided by 8.99 times by 10 raised to power 5 minus 9. So we get 2.5506 10 raised to power minus 8. So this could be like 2.5 10 raised to power minus 8. So just an explanation for the fact that the electric field inside the sphere is zero. We just described that the charges inside the sphere do not move. So there is no acceleration of charges, no motion of charges. So there's absolutely no electric field. So we could say that the charges inside the sphere do not move, as the sphere is positively charged all around, pulling charges in all directions. So no electric field inside sphere. All right. Question number 7. Define the capacitance of a parallel plate capacitor. Okay, so this is a very uh, easy definition. It is the ratio of, so we know that C is equal to Q over V. So charge on one plate, on one plate to potential difference between the two plates. Okay. An initially uncharged capacitor X of capacitance C is gradually charged so that the final potential difference PD between its plates is V, and the final charge is Q. On figure 7.1, sketch the variation of charge with PD for capacitance X as the PD increases. So Q is equal to CV, so basically it would be a straight line because it's a constant proportionality. That's right, direct proportionality over here. So from over here to over, oh sorry, from 0, 0 to this. Right, okay. Determine an expression for in terms of Q and V for the work done on the capacitor X during the charging process. So work done would be the area under the QV graph. So work done is area under QV graph. So half times by QV, simply half times by QV. Another capacitor Y is initially uncharged. The full charge capacitor X and B is now connected to capacitor Y. The capacitor of capacitance Y is 3 times by C. That is that means 3 times the capacitance of capacitor X. Okay. Complete table 7.1 to show the expressions in terms of Q and V for the final potential difference across and the final charges on two capacitors. Use the space below for any working that you need. Okay. Now, to answer this, we need to recall two very major laws that we studied in AS. That were the conservation of energy and conservation of charge. These two, oh sorry, charge. These two led to the Kirchhoff's two laws, current law and the voltage law. So initially, the X capacitor will act like a battery and it will discharge through the capacitor Y. So they are connected in series and in parallel, but from a different perspective. When it comes to the potential difference across them will be the same because they are connected in parallel. But since X is discharging through Y, either like in any direction over here, the final charge, the net charge on both of them will be the same as the initial charge on X. So this is what we have to remember over here. So initially, X, the potential difference across it is Q over C. And Y will obviously have no voltage because it is uncharged. But final X, for this, we need to consider the net capacitance. So we remember this from parallel combination of capacitors that capacitance is add C plus 3C is equal to 4C. So charge in total will remain the same. So when we compare this with a net capacitance 4C, the charge initially will be the same as after because there's a conservation of charge. Charge that has no other place to go from X to Y. So the net charge will be the same. So it will be just same Q over 4C. And for Y, obviously it will be the same also because they are in parallel. So let's write over here because they are in parallel. But when it comes to charge and current distribution between the two, so net charge is the same. So net charge is the same, sorry, initial will be equal to final charge over here. So initial charge is Q, so final charge Qx plus Qy will be the same also. So these two things must add up to the previous, like the initial charge over here. So now how are we actually going to do this? We know that Q is equal, Q is equal to Qx plus Qy. So Q initially was simple CV initially. Qx, capacitance has now become, capacitance is still the same, but potential difference is Q over 4C. Q over 4C, which is just becomes Q over 4. The other also, but with 3C. So 3C times by Q over 4C. Now cancel out the C and C. You can see the distribution between them. So X has Q over 4, 3, like Q over 4, and QY will be 3Q over 4. That's how it actually will become Q itself. So final potential difference would be the same, Q over 4C, Q over 4C. But final charge, like the charge, it will be Q over 4 and 3Q over 4. Now, one thing, we need to show this in terms of Q and V. So C doesn't have to be here. So we know that V, sorry, V initially was Q over C. So we can replace out this by V over 4 and V over 4. So just Q and V, not C over here. So we can delete this over here. All right. State whether the total energy stored in the two capacitors is less than, same as, or greater than the initial energy stored in capacitor X. So to answer this, we just like spoke about the conservation of energy over here, but this was the ideal case. Conservation of energy, this was an ideal case that we used over here. However, for practicals, for practical scenario, there will be some loss of energy over here because of the wires, simply because of the work done to move the charges from this point to this point or this point to this point. So practically speaking, the wires do have some sort of resistance, so some energy will be lost over here. Ideally, they'd have no resistance, so ideally they would like the total energy would be the same as after, before and after, but practically no. So less energy, less energy as before, initially in X. Okay, state what is meant by frequency of an alternating current. So basically just number of cycles. So number of cycles per unit time An alternating current I in a resistor has of resistance 680 ohms varies with time t according to this, where I is in ampere, t is in seconds, show that the period of alternating current is 50 milliseconds. So that is coming from this omega over here. So omega is 2 pi over t equals to 40 pi. So t would be 2 pi over 40 pi. So pi cancel. We have 1 over 20. So 1 over 20 is 510 raised to power minus 2, which if you multiply by 1000 to convert it into milliseconds is 50 milliseconds. Right. On figure 8.1, sketch the variation of I with t between t is equal to 0 and t is equal to 100 milliseconds. Okay, so that means we will have two waves over here. One wave ends over here, second wave ends over here. And they've already given us this function. This is a sine function, so it starts from 0. It will be over at 3.5. So this is 3, this is 3.5. Oh, no, sorry. No. It will be over here at 3.5. It will be 0 over here and minus 3.5 over here. Okay, same cycle repeats over here. Um, this is 3, this is no sorry this is 3, so somewhere over here to 3.5, 0, and back over here again minus 3.5. So this is how we are going to draw that. So let's use this. Sorry. On paper, it will obviously be more refined, but this is a sinusoidal graph, so obviously they're not expecting too much accuracy, but at least the shape should look reasonable over here. So you can make it a little bit more curved over here. So we need to go up till over here. Right. Okay. That's all we need over here. Okay. Determine the root mean squared RMS current in the resistor. So I RMS is equal to I naught over square root 2. So that is 3.5 divided by square root 2. So 3.5 divided by square root 2. 2.474, that is roughly about 2.5 amps. Use the data from B, this B, and your answer in B3 to show by calculation the mean power in 680 ohm resistor is half of the peak power. Okay, so peak power P naught comes from I naught squared times by R, which is basically 3.5 squared times by 680 ohms. Mean power, on the other hand, is coming from the IRMS whole squared times by R, which is 2.5 squared times by 680. The question actually said show by calculation, so we can't just simply use algebra over here. Otherwise, we could use algebra also. but the question clearly said by calculation. If it hadn't said that, we could have used algebra over here. So let's calculate the values. So 3.5 squared times by 680, that is 830, 8,330 watt. And if we change 3.5 to 2.5, we get 4250. So when we take the ratio P naught over P, 830 divided by 4250. So 8330 divided by 4250, that is 1.96, approximately 2, which means that P naught is equal to 2 times by mean power. Or like, oh sorry, the mean power is half, so mean power is half the peak power. All right, so that's our proof. Okay, question number 9. Electrons in a vacuum are accelerated from rest through a potential difference V to form a beam. The electrons each have a mass m and charge q. The beam is incident on a graphite crystal that acts as a diffraction grating. After passing through the crystal, the beam reaches a fluorescent screen. An interference pattern is observed on the screen. Explain what this observation shows about the nature of electrons. Okay, so if you see this one over here, so the interference pattern in the electron diffraction experiment shows that the electrons behave like waves, as only waves can produce such patterns. So this is the characteristic behavior of waves. So we can say it shows electrons behave as waves because interference and diffraction, diffraction are characteristic behavior of waves. Determine an expression in terms of m, q, and v for momentum p of an electron in the beam. Okay, so we know that the work done is equal to qv, and that is equal to the change in kinetic energy. So basically this qv is equal to half m u squared. We can represent kinetic energy in terms of uh, momentum also, that we did it in AS, that is p squared over m. So basically we can represent qv as half p squared over m. So when we do that for p squared, q, we need the p squared subject. So 2qv over m. So therefore p will be the square root of 2qv over m. That's it. The potential difference through which the electrons are accelerated is now increased to a greater value. Describe and explain the effect of this change on the interference pattern observed. Okay, so as we can see this over here, that when we increase the potential difference, momentum will increase, which would mean that the velocity is increasing. And we also know that from the de Broglie law, de Broglie law, that increasing the momentum will decrease the wavelength. Decreasing the wavelength, what it will do is it will change the interference or the interference pattern that we see on the screen. So it will bring those closer to each other. So bring those rings closer to each other. Why? Because if you remember, we had n lambda is equal to d sine theta. So if lambda comes down, the sine theta, which is approximately, you could say, closely related to theta, that also comes down. So the rings will come closer to each other. The radii of the rings will come closer to each other. So that's what we have to do. So increasing accelerating PD increases momentum of electrons, which decreases de Broglie wavelength. Okay, so as a result, the rings seen on screen will come closer to each other. That's it. Okay, so the electrons are now accelerated to different values of V, resulting in pairs of corresponding values for P and the de Broglie wavelength, 1 over de Broglie wavelength lambda. On figure 9.1, sketch the variation of P with 1 over lambda. So we actually already saw over here that P would be is equal to H over lambda. So this is basically directly proportional to 1 over lambda. So it's a straight line from origin. State the name of the quantity represented by the gradient of the line, so that is h, our Planck's constant. That's it. All right, moving on to, oh, okay, 10th question, okay. Radioactive decay is both random and spontaneous. State what is meant by random, state what is meant by spontaneous. Okay, so these are very important questions. These are very frequently examined questions. Let us show you. Uh, wait. Where did it go? Ah, see, this one. So you see, so many years listed over here, like even in the February-March 2025. So random decay means that the decay of radioactive nucleus cannot be predicted. Each decay is entirely independent and occurs with a certain probability over a given time interval. Okay, so we cannot predict when and which nucleus will decay. Okay, spontaneous means that the rate of decay is not affected by external physical factors such as temperature, pressure, or magnetic fields. All right. So the other question was that one piece of evidence for random decay, random nature of the decay. So for spontaneous, we have approximately constant half-life, or the trend roughly looks the same. And for random nature of decay, we have fluctuations in count rate or activity. So that's all we have to say over here. So for random nature, uh, it it cannot be. So sorry. It means that it cannot be predicted when and which nucleus will decay. So each decay is basically governed by a constant probability. So each decay is independent and has a constant probability over a given time. Okay, state what is meant by spontaneous. That means that the decay is not influenced or affected by any external factors. Okay, state one piece of evidence for the random nature of the decay. So fluctuations in activity or count rate. That's it. Describe the differences between nuclear fission and fusion. So I think we also covered that over here. So sorry, let me show you. Okay. So fission primarily occurs with a heavy nuclei. Fusion involves lighter nuclei. In fission, single nucleus divides into multiple smaller nuclei. In fusion, two nuclei combine to form a single, heavier nuclei. Fission is typically triggered by absorption of a neutron. Fusion typically requires extremely high temperatures to initiate. So you can basically write all three if you like, but we just need three. Sorry, right? So we can say fusion. So in fission involves a single nucleus splitting into smaller ones, while fusion involves two nuclei combining to form a single heavier nucleus. Okay, fusion is triggered. Sorry, fission. Sorry, fusion is required. Sorry, fusion requires. So fusion requires high temperatures for initiation, while fission is typically uh, triggered by neutron absorption. You could also say bombardment also. When you bombard neutrons on a nucleus, fission can be triggered also. Okay, explain with reference to the variation of binding energy per nucleon with nucleon number why the processes of nuclear fission and nuclear fusion both release in both result in a release of energy. Okay, so for that we can sketch the graph over here. So the graph of binding energy per nucleon. So binding energy per nucleon, and with mass number it goes like this, where the peak is at 56. So before this, it's fusion, and after this, it's fission, especially with the heavier elements. The question says why the processes both result in a release of energy. Because even when two nuclei are undergoing fusion reaction, so let's say, for example, these two, for example, nuclei undergoes fusion reaction. When it undergoes a fusion reaction, it goes higher up the binding energy curve. Similarly, if you have a nucleus over here, let's say uranium, when it undergoes the nuclear fission, it goes higher on the binding energy per nucleon curve. That means it releases energy. Okay, so we can say that uh, that fission involves splitting heavier nuclei to smaller ones, and fusion requires, or fusion involves, sorry, why do I keep saying sorry? Involves two nuclei combining to form a heavier one. In both cases, nuclei move towards intermediate mass numbers, resulting in release of energy and increased stability of products. That's it. All right. And that's the paper. So hopefully we will see each other in the next paper. If you think I made a mistake somewhere, or if you think some question is not properly explained, If you think I missed out an important point somewhere, please reach out to us and write it in the comments. We will get back to you. All right, so bye bye.